Astroparticle Physics Research Institute, a collection of scientists, universities, and research labs across Canada, who together were trying to uncover some of the biggest mysteries in the universe. And so I'm here today in Kingston, Ontario. I have a PhD studying how galaxies form and change over time, so I'm really looking forward to some of the talks that we're going to have tonight. And I love so much taking these opportunities to share science with everyone, which is like really my favorite part of my job here at the McDonald Institute. So I'm so happy that even during these like really difficult times with COVID, that we're still able to have these really cool events. And all of you people are joining in live or coming to watch the stream after the fact. So hello to everyone joining from home, wherever lands you call home. So again, for me, my home is on the lands of the Cataraqui, now Kingston, the traditional land of the Anishinaabe and the Haudenosaunee peoples, and many indigenous peoples before them. And I'm truly appreciative that we all have the privilege that we have to be able to be here and learn tonight from our respective homes. Personally, I'm a settler from Halifax, Nova Scotia, the traditional land of the skin dressers district of Mi'kmaq, and once the home of the racialized community of Africville. And my ancestors took advantage of these people in the removal of their access to that land. Also, as an astronomer, someone who really revels in the wonder of our land, our planet, and certainly our skies, especially right now, and the universe all around us, I recognize that this science of astronomy really relies on facilities that use traditional and sacred lands to Hawaii and Chilean peoples. And these peoples must be included in the science and become gatekeepers to their space. So I reflect on all of these histories as they are part of my identity and part of the privileges that define me. And so although really difficult right now, while we're online streaming, I like to look around during these events and see who is not here, who in our communities are facing barriers to participation and inclusion. And I commit to helping to remove these barriers in what ways that I can. And I recognize that from my place of privilege, I must listen and learn from those who lived experiences one of exclusion. Science is certainly the pursuit of truth, and this endeavor can't work if society is not treating everyone equitably. So, to all of you, I urge you to think of your connection that you have with your land around you and the privileges you have to learn wherever you are. So let's together reflect on these and work towards the decolonization of these spaces and to make them ones of friendship, love, and access for all those in our community. So, the plan for tonight is simple. We want to make sure that you're home, you have a drink in hand. I certainly have a drink in hand. It certainly helps the science go down. We have 3 talks with a bit of short round of trivia. But before we get started, we have one more bit of housekeeping. First, I would like to welcome on my co-host for the evening, Nick Aurora. Nick, do you want to show your video? You can see if I can actually see.
Hi, Mark.
So many things when you're doing this online to like figure out where everything is on the computer. So Nick, where's your drink?
It's right here. It's a gin and tonic.
Cheers. Very good. So, Nick, you are a PhD student here at Queen's studying galaxy evolution. Nick, you coordinate the Queen's Observatory, and I know that you have an event coming up which you might plug later. And you co-founded Astronomy on Tap with me. Geez, what was it, like 2 years ago now?
Yeah, it's been quite a while. Yeah, it's quite the journey.
Yeah. Especially from the web of pub drink spilling to the online web to the cosmic web that we'll hear about in a little bit.
Indeed.
So Nick,
yeah.
How are you doing tonight?
I'm doing pretty great. Well, first of all, I'd like to thank you for that really deep acknowledgement to us. Yeah, as you pointed out a minute ago, I think we have some strong science and some fun activities in store for tonight. And so it should be a very fun night. We should have all our viewers and all the people who are along with the speaker should have a lot of fun tonight. How are you doing, Mark?
I'm doing really well. I'm pretty jazzed about this opportunity we have over the next 90 minutes to bring a little bit of the universe into our homes. And so I'm pretty excited.
Yeah. Now that we know how we're doing, you got to tell me, Mark, how is space doing?
How is space doing? What is new in space? Well, it's funny you would ask that because the first thing I wanted to talk about today is I hear that the audio is really low at home. So for now, I'm going to talk up and hopefully that helps. But maybe we can find another way to make that a bit better at home. Cool, I hear we're fixing it. So now I'm going to share my screen. And again, I'll try to talk loudly, but my small room might not like the acoustics of that choice, but we'll see. So without any further ado, let's start the event with some space news. So we last were kind of streaming into people's homes back in June. And so what has happened in that time since then? in the world of space. So the first of which is we've been really, really lucky over the last month to a beautiful landscape, or beautiful view in the sky of Comet Neowise. So Comet Neowise has just passed its closest approach early in July, and around the 15th, it was like really, really peaking. And I had the opportunity to drive out of the city and see it, and I didn't quite see this beautiful shot that was captured. But I really, really appreciate it in the sky. Here, this beautiful shot again. You can see two of the tails of the comet, one kind of the dust trail and one of the lighter ions flowing straight away from the sun. And really, really cool thing about comets is they have really, really long orbits through the solar system. Comet Neowise's orbit is 6,800 years, so it's not going to be back for a while. And so somebody has made this really cool shot, I use really a lot because I'm so excited, about what the position of Neowise is over its 6,800 years on the sky as viewed from Earth. And so this big loop, I think you can see my cursor, is going through around here. And that's when it was really close to the sun, but you get all these kind of cool looping back and forth. And that's these retrograde motions that happen. Each loop is 1 year on Earth. And so this is over 6,800 years looping back and forth on the sky as the Earth goes around the sun until it's really, really, really far away and you can't even tell that it's doing that. So it's a really cool demonstration of parallax, which we can even use to find the distance to other stars, but it kind of brings it a little bit close to home. Next in space news, although maybe a little bit closer to home, is some early results point to more success for the standard model of particle physics in respect to the Higgs boson. So I have a picture here of the standard model of physics, which basically shows all of the fundamental particles that make up every single thing in the universe. So we have the quarks that make up protons and neutrons, and we have the electrons and some more exciting things, as well as the Higgs boson. So the Higgs boson was discovered as the most recently discovered fundamental particle, and it explains how particles get their mass. So what's new? Why is it space news? Well, on July 23rd, so just 2 or so weeks ago, on my birthday actually, there was a new paper out of the ATLAS collaboration, which is an experiment at CERN. And what they were finding was one way that the Higgs boson was decaying, particularly into a muon and an antimuon. And so this was something that was predicted long ago, but it's really, really hard to see it because the muon is light. And so for now, we were seeing the Higgs decay into photons or really heavy other particles, first time into the muon. And so far, it looks exactly like we expected, but we still need more data. So please tune in for more. But it's so neat because like the Higgs is apparently how everything gets its mass. And this field, the Higgs field, permeates all of the universe, outer space and on Earth. So just a week later, some other exciting things happened. We went into space to go to another little planet. So Perseverance, the rover, left en route to Mars. So I don't know if anybody at home got to tune in and watch this blast off, but this is the Perseverance rover. The launch was flawless and is now on a 6.5-month journey to Mars. And Perseverance is almost identical to another rover, which you might remember, that went to Mars recently, and that is the Curiosity rover that landed back in 2012. And it landed on August 6, 2012. I remember where I was that day. I was in an auditorium in Arizona watching that 7 minutes of terror that was prepared as it lands through. That we can't communicate with it while it's going through the Martian atmosphere. And so part of that includes parachutes and heat shields and eventually jetpacks and sky cranes. It's a really, really scary 7 minutes. We call it the 7 minutes of terror. And we get to do it all again on February 18th, 2021. And so I think it's going to be landing at about 3 p.m. on the Eastern Coast. So we'll certainly be live streaming that kind of whole reaction. If you remember NASA people, when they got that first signal of a successful landing, they were jumping up and down. We hope to relive it all in 2021. So you just cannot wait for 2020 to be over. Here's another thing to look forward to in 2021. And last but not least in cool space news is SpaceX. I think last time we were here together, we talked about how SpaceX had launched the Dragon capsule for the first time, taking people to the International Space Station. Well, this time we finished that mission. So on August 2nd, just a few days after the trip to Mars started, SpaceX's Dragon capsule came back down, returning 2 astronauts to Earth. They did a splashdown landing. It's the first time NASA has had a splashdown landing in, I think, almost 35 years. Again, it was flawless. Very, very useful Dragon capsule, much more efficient than maybe using a real Dragon where, you wouldn't be able to breathe while riding its back as much as I would love to. But it's really cool. SpaceX is now going to be taking kind of the future role in how we go to and from the International Space Station. So that's it for my space news summary of what happened in the last few months. In our next Astronomy Untitled, we'll have to talk more about the space news now. Next, I wanted to take one moment before we then get on with the talks, which is just highlighting some of our sponsors, which is not the most appropriate right now because usually we're here live in a pub in Kingston, but I'm sure wherever you are, there are similar small little stores that are relying on any opportunity to do business. So try to find those sources. Maybe there's an Astronomy on Tap near you and find out their sponsors as well and find a way to support those places. So, without any more ado, I think I'm going to hint at the next and first talk. So, Kate, I think, Kate, you can show your window. So is there any indication out in out in YouTube land, is the audio better? Are we improving?
Yeah, the audio is much better.
Nick's telling me the audio is much better, so I don't need to yell so much and get really weird reverbs. That's awesome. So Kate, I absolutely love your background. Just for everybody at home, Kate Storey-Fisher is, here's my bio for you, is a PhD candidate in physics at New York University. In her research, she uses cosmological simulations and galaxy observations to understand the composition and evolution of the universe. Kate also writes for the site Astrobytes and organizes around equity issues and in physics and astronomy. Now, Kate, you and I go back, I think it was 2 years ago, I was in New York with you and we got to work together on some educational opportunities. And
yes.
I'm wondering if you're going to tell us a little bit about the image, the really cool shot that you have behind you. Is that going to come up in your talk?
Yes, that'll definitely come up in my talk. You'll learn exactly what this is.
Well, then without any more ado, I'm going to encourage you to share your screen and I'm going to stop sharing the video.
Great. Thank you, Mark. I will share my screen. All right. Hope folks can see this. All right. Hi, everyone. Thanks so much for having me here. As Mark said, I'm Kate Storey-Fisher. I'm a PhD candidate at New York University. And I am really honored to present today at Tap Kingston. So thanks to the Zoom wormhole for allowing me to do that. Although I will say I'm now based in Brooklyn and I'm on the land of the Lenape people. So thank you, Mark, for prefacing that land acknowledgement. But today I want to get into a little bit about what I do with my research. And in particular, I want to teach you how to grow your own universe. So let's get right into it. So this is not a universe. This is a loaf of bread, but this might be quite familiar to you during this time that we're all living in right now. So I first want to acknowledge that this time of the pandemic can be, has been for a lot of us a really trying and devastating time. But a lot of folks at home are kind of coping by DIY projects, so learning to make their own things, to grow their own things. So that's the spirit of growing our own universe today. And I know a lot of folks in particular have been learning to make sourdough bread. I have not yet attempted this, not one of my talents, but I'm going to use this today as an analogy for growing our own universe. So let's say that you go to your favorite bakery and you get this amazing loaf of bread here on the right. And you want to understand this bread. You want to really know what goes into it. You want to know how it has such a perfect crumb, how it has such a nice thick crust. So one thing you could do is you could observe the bread. You could take really detailed observations. You could measure the thickness of the crust, things like that. You could also theorize about the bread. You could sit there and think really hard about what kinds of ingredients go into it. You could write down equations for how fast it rises. But a third way you could understand this loaf of bread is by trying to model it and trying to make your own loaf of bread. So that's what a lot of folks are doing at home. And to do that, you first you need your ingredients. So on the left here, we have some sourdough starter, which you'll definitely need. And you'll need a recipe to turn that starter into dough. And then you'll need the process of how to bake it. And when you do all that, you'll come out with a loaf of bread, and you'll be able to compare that to the loaf from your favorite bakery, and see how you did, and see if you might need to tweak your ingredient proportions a little bit to tweak your process. And in that, you'll get a better understanding of this loaf of bread. So you can probably see where this is going. You can do the exact same thing with our universe. And this is, in fact, exactly what cosmologists do. So what we do is we observe our universe as a whole. So this is an image from the Hubble Deep Field of many, many galaxies in a chunk of our universe that helps us and understand kind of the entire evolution and composition of our universe. But in order to understand that, we need to understand a few things, like with the bread. We want to know what it's made of. So what kind of are the main elements that give us these galaxies in this universe? And we want to understand the process that it took to get there. So in order to do that, cosmologists make models of this universe. So let's get into how we might go ahead and do that ourselves. So first we need ingredients. So it turns out that one of the ingredients, which you might expect, is our normal everyday matter. So that's the matter that makes up stars, makes up galaxies, and also makes up you and me and my laptop and everything we're familiar with. But it turns out an element called dark matter is 5 times more populous than that of normal matter. And dark matter we don't know much about, hence the name dark, but it does have a big impact on the evolution of our universe. It interacts only via gravity with itself and with normal matter, and ends up being a really important ingredient. Finally, we have even more of this stuff called dark energy, which causes the accelerated expansion of the universe. And that also ends up involved how the universe expands. So it turns out, though, that we don't have to worry much about normal matter and dark energy. Dark matter is the main constituent that we're going to worry about for now with our cosmological simulations or our model universes. So let's see how this goes. So we have our ingredient right now, just dark matter mostly, and we need a recipe. So what we do is we're going to take a map from the very early universe. So this is called the cosmic microwave background. And it's basically a baby picture of the universe from just a few 100,000 years after the Big Bang, very young. And what we can do with this is we can understand how the universe might have evolved from its very early state till today. And so here, the blue spots represent colder areas of the universe, where the hotter spots represent warmer areas. The red spots represent hotter areas. And those are the areas that end up evolving into our matter density of the universe today. So what we can do is we can use this as a map for where to put our matter. So we're going to do just that. We're going to take a little box of the universe, and we're going to place our dark matter in the cold spots, which are going to evolve into those regions of higher dark matter density, and eventually our regions of galaxies where we see the matter today. Great, so we don't need the map anymore. We made our little box. You can think of this as our baking dish for our universe. And we'll put our dark matter in there. And the next step is to turn on gravity. So what we can do is for each pair of masses, we can calculate the gravitational attraction between them. And then we can do that for every other pair of masses and figure out kind of the effective gravitational pull on each mass. And then we can move them. So we can roll time forward a little bit and move the masses according to gravity. So you can see if I go back and forth that we have moved each mass by a little bit. And then all we need to do is repeat this, steps 3 and 4, for 13.8 billion years. So luckily, we don't actually have to run this for the age of the universe, but we can kind of speed it up by making each time step, say, 100,000 years, in order to be able to evolve our universe on reasonable timescales. Now, this might seem like a really simple model of the universe. Might just seem, the equivalent of like flour and water for our universe, but it actually ends up working quite well. So the earliest cosmological simulations, back when we didn't have computers at all, were done just this way. People laid out light bulbs on a table, calculated the effective gravity between them, and moved them a little bit, and were able to actually construct a model of the universe pretty incredibly. But luckily, today we do have computers, so we can do a little better. So I went ahead and made a little mini universe using not just one PowerPoint slide, but my entire laptop. And I used, instead of just a dozen chunks of matter, I used 250,000 particles. So each one of these yellow dots is a particle. And I laid them out according to that map of the cosmic microwave background that I showed you at the beginning. So you can see that they're a little bit offset from a grid in just the right way. And then I turned on gravity and let it run for about a week. And this sped up in a little GIF, and it's going to repeat itself. And you can see what happens is that the dark matter particles align themselves in this web-like structure, and that's what we call the cosmic web. So I still find it pretty wild that just some of the right initial conditions and gravity create this entire structure that gives complexity to the universe. But as you can imagine, we can do even better than this. So we can scale this up, and that's what we do to do state-of-the-art cosmological simulations for our research. So this is the illustrious simulation. So I'll start this playing here. And so we've now used 18 billion chunks of dark matter. And this is not on my laptop. This is on a large supercomputer in France. And it's run over 2 months. And this is the result. So you can see the same cosmic web structure emerges just from these particles interacting. And once again, this is dark matter only simulation. So we haven't modeled the gas, haven't modeled the galaxies, yet we get this kind of underlying structure of our universe. So Illustrious is a simulation that I've used before in my research, and we actually actively use a scientist to understand our universe. So let's recap a little bit for our recipe. So we wanted to model this little chunk of the universe. We figured out that we need a map of the initial conditions of the universe as our starter, and we need our ingredients, so normal matter, dark matter mostly, and then a little dark energy. We figured out the process, which is turning on gravity in a little corner of the universe and letting it evolve, and we end up with this structure. And finally, you might not have noticed that this bottom right panel is not the same picture I showed you before. This is actually the mock observations made by simulating how we would observe, like we would observe through telescopes, but through our mock universe, as in the middle panel. And so what we can do is we can compare the simulations of the galaxies in our mock to the real universe. And then we can compare these two, strikingly similar, and we can assess how well our models worked, whether we need to tweak our ingredients, some more dark energy, a little more normal matter, and understand kind of how well we can understand the process of the formation of the universe. So that is cosmological simulations in a nutshell. And I hope I conveyed that it's actually quite a simple process. The scaled up simulations just use a few computational tricks to make it run faster and in more detail. And in quarantine, I was able to grow my own scallions, barely, as you can see here. But if I can do that, then you can definitely grow your own universe on your laptop. So thank you very much.
Yay. Thank you so much, Kate. It's so interesting to hear about this. Do we have any questions out in YouTube land? So in the model, this is from Jack Kraft. In the model is the initial lumpiness of dark matter another variable? What if the matter is like totally smooth?
That's a really good question. Yeah, so the initial map does matter a lot. So if you start with a totally smooth distribution of matter, you're not going to end up with this web-like structure. In fact, you can use the same kind of process, the same gravity, to model everything in the universe. So if you start off with kind of a disk of particles and a nice smooth disk, you'll end up with a galaxy-like structure. If you end up with if you start with a totally flat grid, you'll end up with randomness. So there are parameters that control kind of the exact clumpiness of the initial universe that you need in order to get the cosmic web out.
I see. That's really cool. So it seems like there was some variation in that initial plot, like what we got from Planck of the CMB. Is there like some people using like different, does it matter which part of that map then that you use that's going to change what you get?
Good question. So in the state-of-the-art simulations, we might not use that map exactly because it's going to be hard to recreate our exact universe, but you're going to kind of actually go another meta level and model that map to understand how it was generated, and use kind of different random realizations of very similar maps to create universes. So they're going to have very similar properties, but the exact position of the galaxies, et cetera, is going to be a bit different.
The other thing I found really surprising was like you were only using dark matter Like that's none of the stuff that's in us, and yet it seems like you still end up getting a very good representation of what we see in nature. Like, how important is it to include all the rest of this stuff?
Yeah, that is one of the most wild things to me about these simulations. It's just dark matter, it's just gravity. Obviously, baryons, or what we call normal matter, is really important. So there are whole other simulations that kind of zoom in on a part of this web and simulate all of the gas, the stars, neutrinos, all these other types of particles that go into creating galaxies. And so they definitely are important, and they actually do end up affecting the dark matter, and there's interactions between them. But the dark matter really does drive the large scale structure.
So there's a question from Eric Stacy. Does the introduction of gas between a dark matter and a gas simulation substantially affect the structure you see? Maybe that's a little bit like the question I just asked, but maybe it's different, I'm not sure.
Yeah, I think that was kind of where I ended up at the end of that question. But yes, definitely when you introduce gas, you don't just kind of plop the galaxies right on. It actually does end up interacting with the dark matter because there is gravity between the two. And so one way that we look at different dark matter models to try to understand what dark matter is see how it interacts with gas, which we understand well. And then we can compare the outcome to the kind of galaxies and gas structures that we see in the universe.
So that actually ties into another question by Schon XX420. How does ways that we're discovering the nature of dark matter through other methods, is there any way to feed that into these simulations? Does it have an impact on how this stuff works in the simulations?
Yeah, that's a really good question. So we are kind of attacking dark matter from all sorts. We're trying to do direct dark matter detection. We're trying to do indirect by looking at other astrophysical signals, and then we're trying to model it. And so we can definitely use kind of the things we suspect dark matter might be to input them into our simulation and test if they're real or not. So one example is that we can see if dark matter could be self-interacting. So whether it interacts with itself through some other force we don't know that's beyond just gravity. And we can test different kind of couplings between the dark matter that we might theorize from other experiments and test that in our simulations and see which works.
Last question for right now, but I wanted to highlight that all of our speakers from tonight will reappear at the end of the 3 talks, and we'll have a bit of a total panel where we can take more questions and have more discussion between the speakers, but also with you in the audience. But the last question for right now is Islam Khan's question, which is that you mentioned that you place the dark matter in those cold spots. Like, I guess, based on what you said to one of the other questions, kind of consistently with the way the cold spots are distributed. Why do you put them only where the cold spots? Like, is there not dark matter where the hot spots are?
Yeah, good question. So that's a whole nother talk on how we go from the CMB to where the matter is. But the short answer is that map is the photons of the very early universe climbing all the way to us over 13.8 billion years. And the cold spots are where photons had to spend more energy getting out or getting past lots of matter. So that's why they're bluer, they're colder, because they lost energy trying to get through matter. So that kind of tells us where the matter is. Whereas the hot spots, the photons were able to just shoot right to us. So they still had all their heat and energy.
So you get so much information just from that one shot of kind of the temperature of the early universe. It's so cool.
Very cool.
Well, thanks again, Kate, for now. We'll have you back in a little bit.
Thanks so much.
Thank you. And so now I think I'm going to hand it off to Nick, who's going to be doing the first round of trivia. And I wanted to highlight that in the description of this video, there should be a link to a place where you can start entering your trivia questions, or your trivia answers as we go through trivia. We'll have 2 rounds of trivia, and we'll be having some winners taken from what we receive and be able to send maybe some prizes out to you in the crowd by reaching out to you. But without more ado, Nick.
Yeah, thanks, Mark. And thanks, Kate, for that really amazing presentation about dark matter. Yeah, let's get on to trivia. As Mark pointed out, if you just read our YouTube description, you will see a link to actually go to a form kind of thing where you can fill out your answers. This trivia is essentially divided into 2 rounds, each of them having 5 questions. Some questions requiring more than 1 answer, so maybe some questions are 2 parts. And as always, no looking up at the internet. wait for me to finish the question. I mean, of course, you get to see it online. So if you can read faster than I can, go ahead. And yeah, and the most important of them all, let's have fun. All right, here we go. Once I can figure out technology. Okay, so here we are. Trivia, round one. Okay, so question number one, and this is where Mark will try to come in as well towards the later part of this question because he put in a hint, which I still don't understand. But yeah, what is the name of the comet that was visible through July and will not return to our skies again for another 6,800 years? And the hint is Mark. Waiting for Mark.
So the hint is the Oracle essentially says the opposite of this in the first Matrix movie, and I'll explain that hint when we reveal the answer.
Okay, so once again, the question is, what is the name of the comet that was visible to us throughout the whole month of July, starting, I think, at the start of July, you could see it around sunrise, but towards the end, you could have seen it after sunset as well. It's not going to return to us for another 6,800 years. Hopefully, we get to see it again. You know, it's just on biology to figure out unlimited lifetime. So yeah, name that comet. Question number two. In Star Wars Episode 7 movie, and later confirmed in a 2016 coloring book, the Star Wars galaxy found far, far away was displayed. What type of galaxy was it? Once again, in the Star Wars Episode 7 movie, and later was confirmed in a 2016 coloring book, the Star Wars galaxy found far, far away was displayed. And what kind of galaxy was it? I think later on, our speaker, Connor Stone, is going to talk about the zoo of galaxies, the different kinds of galaxies that actually exist in the universe that sit within those dark matter halos or those dark matter clusters that Kate talked about a minute ago. And so over here, what kind of galaxy did Star Wars Episode 7, and actually throughout the whole Star Wars series, use? By the way, I should mention that the speakers who are sitting in the background can also play this trivia. Not sure we're going to give you prizes, but maybe we will. But you can definitely try and play the trivia as well. Okay, question number 3. And this is a long one. On August 2nd, 2020, SpaceX's Dragon capsule recently splashed down with 2 astronauts on board. It marked the first crewed commercial mission to and from the International Space Station. For this 2-point question, please tell us A, what was the month and year of the very first crewed splashdown from space, and B, how many times has this kind of landing been done since the first one? So once again, SpaceX, owned by Canada's very own, I think, Elon Musk. I think he went to Queens. Had the Dragon capsule come back with 2 astronauts from the International Space Station. And for this 2-part question, please tell us, when was the first time ever in human history where we did such a crewed splashdown? And for part B, how many times since then has this kind of landing been done? Question number 4. The sci-fi Netflix show Dark recently finished. Before I can read on the question further, Mark has sort of piled on and told me how I am behind this TV show scene because I have not seen the TV series Dark yet. So on YouTube, please no spoilers. Okay, continuing with the question. The sci-fi Netflix show Dark recently finished. Dark ties in time travel, paradoxes in quantum mechanics, and a lot more. In Dark, they feature a special particle, which is another name for the Higgs boson. which is responsible for giving all other particles a mass. What is the other name of this Higgs boson particle? In the Netflix sci-fi show Dark, which just recently finished, it ties in time travel, paradox, quantum mechanics, and a lot more. They feature a special particle, which is another name for Higgs boson, which is a particle which is responsible for giving everything a mass. What is the name? What is the other name of this Higgs boson particle? I think this happened in 2007, 2008, when they discovered this particle at the LHC. It was a pretty big thing. All right, question number 5, which will be the last question for this round, is when was the first ever recorded observation of the Perseid meteor showers? So one of the biggest astronomical things, which we sort of left out intentionally from Space News, is the Perseid meteor shower that happens in Canada towards August. And it's happening right now. So if you'd like, the peak is it's about 6 to 7 days long, 3 to 4, 6 to 7 days long. And it was on August 12th, but throughout the month of August, towards midnight, you should be able to see a few shooting stars, which are these meteors from the Perseids entering our Earth's atmosphere. And so the question is, when was the first recorded observation for this Perseid meteor shower? You can guess, and we'll take plus minus 50 years. Maybe that's too big a hint, but we will take plus minus 50 years for your guess. And yeah, if you want to see it at the end of this event, you're all motivated about how cool astronomy is. Step out, look towards the northeastern part of the sky, and you should be able to see the Perseid meteor shower for sure. Okay, so that brings us to the end of the first round of the trivia. We're going to continue with our great speakers that are in place. But before we do, I would like to share with you, I think, something super cool that is happening in and around Kingston with respect to the astronomy. As Mark pointed out, I am the co-coordinator of what is called the Queen's Observatory, and we host monthly open nights. And in this pandemic era, we have, of course, moved that, open house nights. We've, of course, moved that online. And we're now doing space trivia. So if you enjoyed these 5 questions, come and join us for a longer time where we'll do an hour-long trivia, which has all sorts of pop culture references that have space themes and real space questions. So at the end of the day, you do learn quite a bit about space. But along with that, we also showcase, feature some of the Queen's astronomy. And this time we have a graduate student here at Queen's University, Dhruv Bisaria, who's going to be telling us about astronomy in the Marvel universe. So yeah, if the Marvel comic universe interests you've been a fan of the Avengers series and all the other superheroes, come check out the Astronomy Trivia Space Night. And it is on August 19th, which is next Wednesday, starting at 7 p.m. There's going to be a YouTube link. But you can find more information if you just Facebook our names. Okay, so that brings us to the end of our trivia. I'm going to stop sharing my screen, and I'm going to have Connor, who's the next speaker, Connor Stone, if he could start sharing his video and audio. I can hear you fine, and now I can see you. Yeah. So Connor Stone is also a PhD student who studies cosmic variabilities of galaxies. He's the co-coordinator of the Queen's Observatory. So Connor and I work side by side running the Queen's Observatory, the public outreach program there. But in the past, Connor has worked on various dark matter detection experiments situated at Snow Lab. Connor also runs the physics graduate student seminar, and as a hobby, he does not go away far from astrophysics and loves to do astrophotography. I might add, Connor just sits right behind me in our office. He shares an office with me. We're in the same research group as well. So yeah, I can't wait to see what Connor has to tell us today. So Connor, please go ahead and share your screen.
All right. I should note that we haven't been in the same office for the last few months.
Well, soon enough, my friend, soon enough.
All right, so hello everyone, I'm Connor, and as Nick said, I study the cosmic variability of galaxies, which is pretty broad as a topic. So I thought I would focus in on one subtopic of that, which is galaxy morphology, or more simply, what galaxies look like. And the universe is filled with, let's see if I can hit next slide. Oh. There we go. Okay, the universe is filled with lots of interesting looking galaxies. And as an astronomer, I need to find a way to categorize these galaxies and organize them, which with all of the different shapes that are out there is quite a challenging thing to do. So what do astronomers do first? Well, the first pass at classifying what a galaxy looks like is the Hubble tuning fork. And that's what we're looking at right now. This gives us a quick way to organize the shape of the different types of galaxies that we see. On the left, this E0, that's an elliptical galaxy. Those are essentially balls of stars all swirling and swarming around each other in all sorts of chaotic different directions. There can be billions to like trillions of stars in there. So these can be quite big galaxies. And as you go along, the numbers sort of tell you how flattened the galaxy is. They end up sort of looking like a football shape. And these are just other types of elliptical galaxies. Eventually, you get flat enough that it's not so much a football as more of a disk, and that's where you get to the twin arms of the tuning fork, where these are different types of spiral galaxies. So some spiral galaxies along this top arm, they have these nice big spiral arms that kind of come out from the center. And the spiral arms are more tightly wound here than they are here. And that's sort of how you specify where along this arm you are. You can see these ones really tightly wrap around the galaxy, whereas the spiral arms coming off this one are sort of almost pointed away from the galaxy. Similarly, on the bottom arm of the tuning fork, there's spiral arms here, but right in the center, you'll see a sort of straight feature, and that's called a bar. So these are barred galaxies, and then often a spiral arm coming off from the end there. So these sort of give you the basic categories of galaxies that are out there in our universe, but this is really a first level classification. There's lots of wonderful and weird galaxies out there. For example, a galaxy disk doesn't need to be a perfectly straight galaxy disk. You can have a warp in the disk, and categorizing that might be a little trickier. You can also get galaxies colliding with each other and sort of spraying out arms of stars and gas. This galaxy collision can cause all sorts of different weird shapes that galaxies can have. And aside from colliding, galaxies can also just overlap. These two aren't colliding. One of them is much further back than the other, but they overlap in just such a way to create what we call a butterfly galaxy. It's sort of got two wings to it. These are very pretty, but very hard for an astronomer to sort. There's also some very special objects like these ring galaxies, where the center is this like core of a galaxy, there's a gap, and then essentially a disk of gas and stars around it. And So this is a whole other type of galaxy. And of course, you really like these galaxies, so you say, if you like it, then you got to put a ring on it. All right. So all sorts of different types of galaxies out there, and organizing them can be really challenging. It is a very hard problem to get a computer to sort all these different types of galaxies. And so that's actually where citizen scientists can come in. So Galaxy Zoo, the Zoo of Galaxies, is a website where anyone can go log in and categorize galaxies for astronomers. And this actually helps us a lot. There's been about 1 million galaxies so far that have been categorized over the last 10, 15 years by Galaxy Zoo citizen scientists. It's very easy to do. It takes less than a minute to do one. So you just go onto their website and they'll show you a picture of a galaxy and give you some options to pick from. This one looks like a smooth galaxy in the center, and there's another little galaxy on the side, and that one we would just try and ignore. Now that's something that we are very good at as humans, but a computer would have a very hard time with this picture because it might get confused by these sort of strokes coming off of that star. It might get confused by having more than one galaxy in the image. And also this one has a dot right here that might make it think that's the center of the galaxy instead of the actual center here. But humans, this is no problem for us. And so humans are right now the best way for us to categorize galaxy images, and there's just not enough astronomers to sort the millions of galaxies and images of galaxies that we have out there. So Galaxy Zoo has been really, really important for astronomers and actually has been connected with over 400 scientific papers, and lots of discoveries have come from Galaxy Zoo and people who have by eye looked at all sorts of galaxy images. For example, there's this one object that was discovered. Oh, it's taking a little bit to load. This one object that was discovered by looking at one of these images. Someone noticed, a school teacher from, a Dutch school teacher, noticed that there was this sort of fuzzy green patch underneath the galaxy. And further study by some scientists revealed that this fuzzy patch here wasn't a problem with the detector. That was real gas out there in the universe that we shouldn't have been able to see. But this galaxy had a period of activity, blasted out a bunch of light, and lit it up for us to see. These are very rare and special objects that we didn't even really know existed until someone saw it with their own eye and realized that it was special. And the person who noticed it actually ended up on the scientific paper, Henny van Arkel. She ended up on the scientific paper announcing its discovery. And the object was called Henny's Warwarp in her honor, which I think is pretty cool. And it really shows how important the citizen scientists are to these astronomy endeavors. All right. So with Galaxy Zoo, astronomers have been able to identify over 1 million galaxies, but we have an issue. Looking at this image here, this is the Hubble Extreme Deep Field. It's a very tiny patch. I think it's less than 100th the size of a full moon on the sky. And this tiny patch has all sorts of galaxies in it. Essentially every dot that you're looking at here is a galaxy, except for, see these stars, how they have that kind of cross on them? That's a star. But just about every dot you're looking at is a galaxy. In fact, there's about 5,500 galaxies in this image. And if you take 5,500 galaxies and the size of this patch, which is just 1/32 millionth of the sky, you realize that there's probably around 200 billion galaxies out there. And that means that even at the rate that Galaxy Zoo is going, it would probably take millions of years to classify all the galaxies that we have out there. So while humans are the best we have right now, we can't rely solely on humans to analyze all of the galaxies that are out there. And that's where machine learning comes in, which is one of my favorite subjects. So machine learning is being used in combination with Galaxy Zoo to reproduce the galaxy morphologies that we see out there. And the way that it works is sort of through an iterative process. A human looks at a galaxy image and clicks on the parameters that identify that galaxy. Those are fed into a neural network, and then that neural network feeds in and tries to make its own predictions for that image. This cycle continues over and over and over again until we end up with a neural network that can consistently predict what the parameters are for a given galaxy. We're not quite there yet, but for many galaxies, it can do a very good job, which means that if you go onto Galaxy Zoo nowadays, you won't see very many simple images. You'll see more complicated images, and I think more fun and more beautiful images. So here is an example where on the right side, you won't see very many of these galaxies that are kind of just elongated blobs, because the algorithm is pretty quick at figuring those out now. But you will see more of these interesting ones that maybe have two galaxies on top of each other, or maybe they're a little lopsided, or just a little fuzzy and kind of hard to figure out what's going on in there. So you will actually get to see some more interesting galaxies now. If you go onto Galaxy Zoo, you can really quickly look through a whole bunch of them in some spare time, and you can help out astronomers like me understand more about all the different weird types of galaxies that are out there. So thanks for listening, and I will see you in the panel discussion.
No, Connor, don't go away. We still have a few questions for you.
Oh, okay, yes.
Yeah, thank you. Thank you for that really great talk. Yeah, let's talk about the Hubble tuning fork. We can go all the way back to the Hubble tuning fork. And
yeah, let's see if my computer will do that.
and one of the biggest questions that some of the viewers might be asking is that if you look at this tuning fork, it looks like galaxies start at what is E0, and somehow by the end of their time end up as irregular or IRR. Is that really true? Do galaxies really evolve along this arm?
You're preempting something that I intended to say but forgot / left out due to time constraints. So originally, astronomers thought that these galaxies were how all galaxies started. The E stands for elliptical, but it can also mean early type, which is what astronomers used to call them. And they were called early type because they thought galaxies started as these big balls and then collapsed down to form these spiral galaxies. The truth is far more complicated, and if anything, it goes the other way. But really, what we think now is that lots of smaller galaxies collide together and slowly build up to make larger galaxies. And depending on how those collisions go, you can either end up with a lot of small collisions sort of building up momentum and giving you a nice spiral galaxy, or you can have big collisions that completely destroy this fine and detailed structure of spiral galaxies and leave you with big, messy elliptical galaxies where all the stars are going in every direction.
Right. Oh, thank you, Connor. There are more questions about just the Hubble tuning fork itself, but maybe we'll keep that for the discussion later. For now, we can just move on to Galaxy Zoo. And Fred Sunderman asks about how multiple untrained observers agree on classifying objects on Galaxy Zoo.
Right. So Galaxy Zoo is very clever, and they don't just show each picture once. They will show the same picture of a galaxy, like this one. They'll show this same picture to many different people. So you can make your best guess at what this galaxy should be. And they encourage you to just try your best and don't worry too much about getting it exactly right, because they will have many people look at that image, and eventually the true answer will sort of reveal itself. And sometimes their categories aren't detailed enough to specify an individual galaxy, and they'll know that they've made a mistake or that they need more categories if people keep switching between two different categories. And so they'll know, well, it's got to be somewhere between those two. We don't have a category for that yet. So they suggest you just do your best. And over time, many people will look at the same one and give them a good sense of what the true nature of that galaxy is.
Yeah. So essentially the law of averages, so to say, working out over here.
Yes.
So thanks, Connor.
Yeah, you don't need to worry
Go
about
ahead.
being as good as a professional astronomer at picking out all these different types. They ask you very clear questions. They have a little explainer off to the side. So anyone can take part in this and help us astronomers out.
Yeah, I mean, yeah, I do it, and I think this is a pretty fun activity to go through. And yeah, I think this was a very good plug. Thanks, Connor. And yeah, thank you for this great talk. We'll see you back here for the discussion where I have lots of many more questions about galaxy evolution and how to classify galaxies properly.
All right. So
All right.
Should I stop sharing?
Yeah, stop sharing your screen and your video. Mute yourself. Okay, so that was a really great talk by Connor. Connor did an amazing job, but it's time to keep moving on because the show is packed with science and fun for you. So we're going to continue doing trivia. So this is the second round of trivia. And once again, there will be 5 questions here. And if you would like, if you haven't already, I would ask you to follow our YouTube link or YouTube description. There's a link there where you can fill out questions, answers to the questions that appear over here, and we will do the reveal later on. But for now, moving on. Question number 6. What is the name of the rover recently sent to Mars, which among other things, collects a sample to be eventually be returned to Earth? What is the name of the rover that was recently launched to Mars, which among other things, will collect a sample to eventually be returned to the Earth? I think Mark talked about this a little bit, very briefly, during Space News. So I think we're giving you hints, and maybe this is a freebie over here. So name the rover that was recently sent to Mars, and it will return a sample from Mars to Earth. Maybe Mark later on will tell us how it is going to do that particularly. Okay, question number 7. Subsurface oceans have been known to exist in many moons in our solar system, including Jupiter's Europa, Ganymede, and Saturn's Enceladus. Astronomers have now detected evidence for a subsurface ocean on a different solar system object. Name that object. So once again, there seem to be quite a few oceans, just not on Earth, but on other objects within our solar system as well. Some of them are Jupiter's moon Europa and Ganymede, the so-called 2 of the Galilean moons, and also on Saturn's Enceladus. Astronomers have now detected evidence for subsurface oceans on a different solar system audience. Name that object. Question number 8. In 2008, the Hubble Space Telescope took the first ever visible light image of an exoplanet. What was the name of that exoplanet? So in 2008, Hubble took the first ever image of invisible light of an exoplanet. What was the name of that exoplanet? And just discussing this question with Mark, Apparently, this object is not just the first ever exoplanet to be imaged in visible light, but it's still a point of contention. It is still very much something that researchers are actively, in the world of exoplanets, actively studying. So once again, the question is, in 2008, Hubble Space Telescope took the first ever visible light image of an exoplanet. What is the name of that exoplanet? Question 9. This is also another Hubble Space Telescope question. Which NASA space shuttle carried the Hubble Space Telescope to orbit in April 1990? So this year, Hubble celebrates its 20-year anniversary of working hard in exploring or revealing the universe to us. And name the NASA space shuttle that actually carried the telescope into orbit in the year of 1990 in April. And finally, the 10th question. Christopher Nolan's next blockbuster, Tenet, is finally getting its time in the theater after a COVID-19 induced hiatus. In this movie, it seems like people can reverse time. Typically, Star Trek uses a hypothetical particle with an imaginary mass that travels faster than light to explain anything to do with time travel. What is the name of this particle? I just realized I made a math error. It's now the 30-year anniversary, not the 20-year anniversary of the Hubble Space Telescope, which went up in orbit in April 1990. So thank you, Fred Sunderman, for correcting me on that. Anyways, the last question. Christopher Nolan's next blockbuster, Tenet, is finally getting its time in theaters after a COVID-19 induced hiatus. In this movie, it seems like people can reverse time. Typically, Star Trek uses a hypothetical particle with imaginary mass that can travel faster than light to explain anything to do with time travel. What is the name of the particle? Name this particle. All right, so that brings us to the end of our trivia fun. We have one more great speaker lined up for you. That's going to be Dr. Sarah Schon, and I think I have to stop my share and bring back Mark Richardson, who's going to be introducing Sarah. So Mark, take it away.
Yes, and thank you for doing the trivia. I think all the long questions were mine and convoluted to include pop culture and science and all that fun. But not last but not least, I would love to welcome Sarah to share her video and her audio and introduce her. So our final speaker tonight, before everybody will get to come back in the panel, is Sarah Schon, Dr. Sarah Schon. So Sarah, you did your undergraduate degree at the University of Auckland before going on and doing your PhD at the University of Melbourne. Mm-hmm. Your first postdoctoral fellow position was here at the McDonald Institute, is here at McDonald Institute at Queen's University. And so, Sarah, you mostly study how we can constrain dark matter using astrophysical systems and objects, presumably like galaxies and weird-looking galaxies at that.
Yes, how convenient.
So
it's almost like we planned this.
It's almost like we planned it. So I can't wait to hear about how galaxies look wrong. And apparently, we've now heard from Connor that galaxies are expected to look a certain way. So I'm looking forward to your talk. So you can share your screen.
Okay. There we go. Does it look right? Okay. So thank you so much for having me, and thank you everyone for staying in to join us this evening. Thank you so much for Mark for the land acknowledgement at the beginning of this session. It kind of made me think that, as Mark mentioned, I did my undergraduate in Auckland and my PhD in Melbourne, and both of those are colonialized countries as well. So I want to acknowledge Ngāti Whātua Oraki, who were the traditional owners of the land in Auckland, and the Wurundjeri and Boonwurrung people in Australia, who were the guardians of that land. Right, so onto this talk. So does this galaxy look weird to you? So we've had two very excellent talks already this evening, talking a little bit about how we model galaxies and also how we try to classify galaxies. And so as a kind of perhaps point of difference, I'd maybe not talk so much about the methods and the results of this method, but maybe a little bit about the method itself. And since I study dark matter, I'm going to be focusing on that. So yeah, let's look at weird galaxies and what it tells us about dark matter. So let's start with a question. How do we recognize when something is wrong? So now I realize this is a somewhat ambiguous question, and if I get this correct, social scientists actually tell us we're actually not incredibly good at telling if something is wrong. But considering we're coming at this from an astronomy point of view, it kind of allows us to kind of, you know, constrain the question a little bit. And so what does it mean when we do science and we look at either data or a model and we realize it's perhaps incomplete or a little bit ambiguous or inaccurate, or there's just something that's not quite right, there's room for improvement. And so maybe to illustrate this a little bit further, I thought I'd start with this. And so here we have a representation of the essence of cow. So let's just imagine there's an objective true object, which is a cow, which I suppose philosophers might dispute, but let's just go with it. And so let's look at this representation of a cow. And so most would say it's pretty good. I mean, you know, it's recognizable. The colors seem about right. It's got the right number of legs. It's hanging out in a field somewhere. So you're like, yeah, that's pretty good. On the other hand, if you're more perhaps biologically or anatomically inclined, you say it's kind of a weird square shape. It's kind of very blocky. And so we might be like, okay, so maybe whoever made this hadn't seen enough cows in real life. But then I could tell you that actually around the 19th century in Britain, this was all the rage. There was like this whole genre of super square looking livestock. And so we actually now realize that the particular choices of this artist to kind of depict it in this square shape wasn't because they didn't know what a cow looked like, but because this was actually a representation of status. And so I guess the point I'm trying to make with this very convoluted metaphor is that the way we model things is never complete. So unless we have, I mean, perhaps it is possible to create a perfect one representation of an object, but most of the times our models are incomplete and perhaps they're meant to depict a certain facet of the object. And in this case, the facet that we're trying to get at isn't necessarily something tangible, or, you know, some things are perhaps not visible, you know, in some ways or in others. And similarly, we're constrained by the medium of our models. In this case, this is a 2D painting, and so we don't have any kind of appreciation of what's inside the cow or the behavior of the cow, what the cow was doing, you know, 10 days ago. So, you know, kind of keeping that in mind and kind of, you know, thinking about the relationship between how we represent things and the thing in itself, let's go and talk about galaxies, because that's what we're actually here for. So let's think about then, you know, I mean, most of us are fairly familiar with what a cow is meant to be, but galaxies are a little bit more esoteric. So it's like, how do we get to this idea of what a galaxy actually is, and what does it tell us about the rest of the universe? And so if we kind of go back, and I'm going to go on a tangent here, so if I run over, Mark, just kick me off. I kind of realized that when we kind of tell these stories, they very much come from this very westernized perspective. So here I put up, you know, the word galaxy comes from the Greek galaxias kyklos, which means milky circle. But in reality, of course, all cultures have some sort of astronomical tradition. And so I think, you know, this is kind of for myself as well, this call out to myself, we need to acknowledge that, you know, when we tell these stories about astronomy, we don't just tell the Western story. These stories are ubiquitous, and we need to acknowledge that, you know, this truth exists in different cultures, and these are important too. But let me just stick with this for now. And so perhaps, you know, back in the day, more than now, since we're kind of stuck with light pollution, we could see this kind of milky, you know, structure across the night sky. And so obviously the first kind of models of this wouldn't have been very much scientific models, but they would have been sort of narratives of mythology, because they were then the most, you know, prominent structures of how to explain why the world looks like it does. But we can already see that relatively early on, so if you look at the Greek philosophers, and also in particular Middle Eastern natural philosophers, there was already some speculation that, you know, hey, maybe this isn't some kind of remnant or some nasty bodily fluids of some deity. Maybe this is actually, you know, an amalgamation of stars. And then there was some debate about how close this is, how far away is this, and there was actually some arguments with parallax saying, well, actually, it doesn't have parallax, so it actually has to be quite far removed from where we are. And so from there, and then obviously, you know, science evolves around that, and it allows us to kind of make more kind of accurate speculations about the universe. And so, you know, we kind of get to the point where, you know, Galileo actually observes this with more sophisticated technology like telescopes and says, actually, yeah, these guys were right. This thing is made up of lots and lots of stars. And so suddenly we go from, hey, this is a story, to this is actually a physical object. And it's not actually as alien as we think it is. It's you know, it's kind of made of the same stuff as our sun. And that's something that we're very familiar with. And so then we get kind of Herschel trying to map out the sort of, you know, early Milky Way. And you kind of see right at the center is this, the solar system. And then, you know, if we skip ahead quite a bit further, we get the sort of first pictures of, you know, extra Milky Way galaxies. So this is an early picture of the Andromeda galaxy, and that really shifted this focus from this eternal, you know, Earth-centric universe to, hey, we are just at a really insignificant spot, and, you know, we're going to go from this sort of perhaps more theological, philosophical framework to, you know, this is science, and everything can be understood in terms of these natural laws. So we're going to kind of skip a lot of these kind of nitty-gritty interesting details, but I just say it's sort of the birth of modern cosmology, which is very exciting. And with it kind of came this idea, like I mentioned, now that we kind of have this foundation of the natural sciences to explain, you know, what galaxies are. And obviously with better and better telescopes, we can, you know, start to look at not just nearby galaxies like Andromeda or the Magellanic Clouds, but we can look at lots and lots of galaxies. And suddenly there, we realize there's lots and lots of these things out there. And, you know, as we get better and better pictures of these, we can kind of start to fiddle with, or, you know, look at the anatomy of these. And so, you know, at this point, we're feeling pretty good about ourselves. We're like, okay, so we've got stars and we've got gas, and we know that, you know, gas collapses and it forms hot things. And, you know, we know about gravity, and that kind of holds everything together. And, you know, everything was looking pretty good. And then we hit a major snag in the mid-20th century. And so, of course, this is the story of Vera Rubin, and I couldn't be giving a dark matter talk without mentioning her. And so what she did was like, okay, so we've got our dark matter model, and we don't have a dark matter model, I'm skipping ahead. So we've got our galaxy model, and we kind of like, okay, so we can actually make out, you know, we can start to make out the motion of individual stars in these distant galaxies. And so at this point, we're like, okay, everything is gas and stars and dust and God knows what. And we kind of have a good expectations knowing, you know, how physics works and how gravity works about what we expect the motion of these stars to be. And so in the plot at the top, you can kind of see the sort of disk and the gas curves. And this is what you kind of expect the kind of velocity distribution to be if that were indeed the case. And so Vera Rubin looked at lots and lots of these galaxies. And to everyone's amazement, that's not what was happening. You know, this kind of very simple model, which was built on assumptions which were, you know, very much confirmed and very much established, suddenly wasn't turning out what we expected. Instead, we see this kind of top, you know, the little squares, the little markers, and we kind of see as like, hey, actually, there is, you know, there's something there that we can't see. And the good thing here is that it wasn't just one galaxy. So here is this kind of this tension between, well, if we have one object, how much does it really tell us about all the other objects? But it wasn't just one, it was mostly the entire population. And so in this case, we're like, okay, so, you know, we have to work on all these assumptions we had about what galaxies are made of and how they actually function. And then we come to a bit which I like to call particle physics shenanigans, which is also a really, really fascinating kind of, you know, few decades of physics research, but unfortunately we can't cover. But the gist of it basically is that, you know, this dark stuff, this extra stuff in these galaxies isn't just something which is difficult to see, it's something completely different. And that brings us to kind of, you know, the sort of modern picture of the standard model and, you know, our energy matter content of the universe, and this kind of very distinctive breakdown where, yeah, most of the stuff is actually not, you know, the usual gas and baryons, it's dark matter. And that really kind of spelled the kind of beginning of how we build really comprehensive dark matter galaxy models. And so here we already had Kate's excellent talk about explaining how we can grow our own universes. So here is an example of Gadget, which is one of these codes, and you can kind of see the grid and, you know, where you form structure. But then also more importantly is like on the other side of things, our ability to observe the universe to, you know, when forward in leaps and bounds. And so we weren't just seeing the really obvious big things, we were seeing the little things and the faint things and the really, really weird stuff. And sometimes those are actually, you know, both of these components are important because you need to explain the general behavior, but you also have to be able to explain the weird stuff. Otherwise, it's not a very, you know, it's not a complete model. Okay, so everything was really going really, really good. And like we heard from Kate, you know, just plugging dark matter into this gravitational box gives you really spectacular results. It kind of gives you the overall structure, and it gives us, you know, pretty good, you know, appreciation of the kind of different masses we should expect. And, you know, everything was pretty good in galaxy formation land for a while. But then, as per usual, physicists' penchants to nitpick kicked in. And we realized that, you know what, this was good. There was definitely room for improvement. And so here on the right, we have a snapshot from like a zoom in from the Millennium simulation. And so this is just dark matter. And so you can kind of see this is one halo, and the really bright thing at the center is where you would form the galaxy. But as you kind of notice, it's not entirely smoothly distributed. You see these little clumps surrounding it. And so some of these is what you would expect to be satellite galaxies. And so this is perfectly normal. Our Milky Way has a whole bunch of them. And so initially people were like, yeah, this is great. This looks like what we want. And then people started to be like, okay, well, let's look precisely at, you know, what the stuff is doing. How many of these satellite galaxies are there? And what exactly is that distribution of matter? And this is where some very early challenges to these n-body dark matter only simulations arose. And so one of them is what is called the cusp core problem. And so that basically relates to the fact that if you look at where the dark matter is in one of these halos, which host galaxies, you notice that the density increases towards the center. But in particular, all these n-body simulations predicted that there's a lot of dark matter at the center of these halos. The problem, of course, was that when we looked at, or we tried to, you know, look at what the mass distribution is in actual galaxies, we didn't just see cusps. We saw a lot of, you know, chord flat things, or, you know, things were all over the place. And so we're like, well, this is a problem, because this, you know, the outer parts are fine, but the inner bit definitely needs some work. And then secondly was that, you know, these n-body things produced a lot of satellites. But if we looked at the Milky Way at the time, we showed like quite a few of the kind of big things, like the Magellanic Clouds and so on and so forth. But a lot of the little things that were predicted just weren't there. And people were worried, oh, well, are we overproducing small structure? And so, yeah, so that was definitely an issue. And so if you kind of, you know, address, you know, are presented with this problem, there's two ways to think about it. The first, obviously, is to say, well, you know, like we heard, a galaxy isn't just dark matter, it contains gas as well. You know, this doesn't have gas in it, but what, you know, maybe that will fix it. But then if you're someone like me who likes dark matter, we get very excited, because every time something goes slightly wrong, we're like, hey, maybe dark matter does something more fun than being gravitationally attractive to things. And so one of the sort of exercises that we're sort of engaged in was throwing different dark matter models at it to see whether you could rectify that situation from that side. And so when we talk about dark matter in the context of n-body simulations, they're really these cold collisionless, you know, particles. And so they don't really have any real one-to-one relationship to any one specific particle model from a sort of fundamental physics side of things. So you can certainly write down a model which has those properties, but inherently simulations are fairly agnostic about, you know, how this ties into, you know, some complete theory of, you know, the universe and everything. It just has these kind of basic properties. And so we could very easily come up with things which, you know, are still mostly cold and collisionless, but there's sort of wriggle room, and they might have a few different properties. And so, for example, we can think of something like warm dark matter. And so it has just a little bit more energy. And what that actually does, it wipes out a lot of that small structure, because they're just not, you know, they're energetic enough that it kind of overcomes the gravitational binding. And so you can knock out a lot of these little structures, and that could potentially solve that problem. You could think about self-interacting dark matter, and so this would include some sort of internal friction to when you form these objects, and that could actually core out your halo. You can think of something like fuzzy dark matter. And so this is something which is so small that you can't actually model it in an n-body simulation. You have to come up with some complicated wave description. And if you do that, you can actually produce cored things as well. You can go super exotic and think of mirror dark matter. And so this is something where you don't just have a particle, you have an entire dark sector. So you can kind of think about baryons, except we can't really see them. And so you get some really cool, funky things happening there. You could think of things which are annihilating. So that basically means the particle is its own antiparticle. And, if they run into each other, they go boom and release energy into the system. Or, get things which decay in some kind of fun way. I've kind of put the bring your own dark matter model. So this is definitely not exhaustive. Particle physicists are some of the most creative people on the planet. And so they're always coming up with new and exciting things. And so there are definitely options to, to try to fix those problems. So for once, my hopes and dreams were answered. We had 2 excellent talks which mostly covered this. So, of course, from the other side of things, like already mentioned, perhaps one of the most obvious things to try to fix these problems is just to add gas to those simulations. And obviously, our computational capabilities have improved vastly since the first n-body simulations. And so now we're actually much more capable of running full hydrodynamical simulations. And so here we actually see an output by Illustris, where you see we're actually forming nice little galaxies. Similarly, we have far more complete observations. And so part of the problem of us saying, oh, well, maybe we don't have enough satellites was, well, they're actually hard to see because they're very small and they're very faint. And so, now that we're much better at, knowing what we're looking for, actually having targeted searches and, things like galaxies are certainly being helpful in terms of finding, these extra weird things or, perhaps even small things. And so that has certainly, changed the picture as well. And so how does this change our wonderful hope of trying to kind of figure out what dark matter actually is? Well, it closes down the parameter space where, you can fit fun new dark matter properties in. So if we have more complete observations, means the problem wasn't as bad. And on top of that, we also have complementary dark matter constraints. So obviously, if you have a dark matter model, it can't just explain what halos look like. It has to make sure that the CMB, the cosmic microwave background, doesn't get upset too much. Or it has to potentially be detected in, terrestrial detectors like, like Xenon 1 ton or whatnot. And so, having extra science and better observation certainly closes down this parameter space a little bit. But then on top of that, if you actually start running these n-body simulations with the correct gas physics, it also has an impact. So for example, if you look at AGNs, so that's what you call an active galactic nuclei. It's kind of like a black hole, and when things fall into it, it gets very violent. And so you have these massive outbursts of energy. And for example, in smaller ones, you perhaps don't get an AGN, you get a supernova. And the kind of if you expel a lot of like matter and energy, that can also change what your particular halo profile looks like. So that has certainly helped in alleviate that problem. Similarly, star formation. And so one of the tricky things here is that n-body simulations don't, because you're trying to simulate the entire universe, you can't put individual particles into your box of the universe. So when we talk about a particle in the context of simulations, we usually talk about something which is, tens if not millions of solar masses. And so when we try to model star formation, we have to have some sort of prescription that fits into this. But even putting something fairly semi-analytic into this also helps solve some of these problems. Putting an actual gas component, like mentioned, it has an additional gravitational part. And so that also alleviates some of these. And lastly, something perhaps a little bit more subtle, and this is this idea of greater resolution. And so if you're in a, sorry, I'm probably going over. If you're, in a simulation and you chop up things finely enough, that also changes the output. And so at this point, you're probably thinking that this looks very messy, and this is in part because I'm not very good at graphic design, but also because it actually is very messy, because you have all these components which are modeling very complicated physics, and now you're trying to negotiate which of this is the gas physics and where is there actually still room for dark matter. Okay, so I'm going to go really quick for this. You're probably saying you've been complaining about this a lot. I don't hear you doing anything to solve this. And so in my defense, I can say that, well, okay, so maybe, considering that physics in galaxies is very complicated, you can perhaps think about some of these processes at high redshift. So, if you think about the first stars forming, you get small halos, gas falls into it, and then eventually you form stars. And so this is relatively straightforward because, it's the first stars. You don't have AGNs and you don't have, all the messy other stuff going on. And ideally, when you have then dark matter actually doing something to the gas, you might have things happening like, so if you've got annihilating dark matter, you're heating up the gas, and so perhaps what happens is that you perhaps don't form anything at all, or you form less things, or you form them later, or you form them differently. So maybe the stars are different sizes, or maybe you even form something super exotic like a dark star. And then the hope is that with future observations like 21 centimeter or the James Webb Space Telescope, we can then observe these very early epochs of the universe. And if dark matter has an impact on star formation, then it might be much easier to isolate that from the really messy gas physics that goes on at current times. And so I apologize for going over, and I thought I'd just leave you with what my average day at work looks
like. I love that picture so much. I also wanted to highlight that here is a beautiful example of an AGN. In fact, my favorite AGN is active galactic nuclei from Centaurus A. Sarah, thank you so much for a really, really, really interesting talk. And yes, I'm sorry to maybe make you rush a little bit at the end.
No, I apologize.
We are going to have a bit of a panel to chat, but I will ask you just one question, which I think you tied into this quite well after the question was asked, but maybe you have some commentary to add. So Stephen Yanagisawa, he asked, do some galaxies orbit other galaxies like planets orbit stars?
Oh, right. So in the short, yes, perhaps. So the nature isn't quite the same. So it's not like you have the central star and then you have these constant orbits of planets. So most solar systems are fairly stable things. So generally the Earth will stay on its orbit short of some sort of catastrophic, impact event or, something else happening. Actually, that's perhaps an assumption. Maybe I'm assuming just because ours is fairly stable. We don't actually, we've got to observe more, and this kind of ties in. We need more observations to make these assumptions. But yes, so when galaxies form, we kind of call this hierarchical kind of formation. Those I talked about at high redshift. So high redshift means like long, long time ago. And so these small things will form first, and then they grow either through more material falling into it, because you recall that kind of beautiful web structure that we saw in Kate's talk. And so along these filaments, matter is moving, and so things will fall into the halos, and they grow that way. But they also grow through these things called mergers, and so that happens with two halos collide, and then they kind of make a whole mess, and then eventually they settle into a bigger halo. But but depending on what you actually end up is somewhat dependent on the original sizes of the relative things. So if two things which are roughly the same size meet, you end up mostly, this is somewhat mass dependent as well. You mostly end up with a bigger blob. But if you, for example, have something Milky Way size and something really tiny, like a dwarf galaxy falls into it, and then you might have this sort of thing where you have this gravitational thing falling in and sort of might potentially slingshot around, and you kind of produce some sort of orbit. And I think Mark will already be able to answer this better than me. And like depending on also where the gas is and the properties of the dwarfs, in some cases you actually start stripping the material off the dwarf, and so you lose stars.
Talk also featured that, right?
Yeah,
he showed some of these cool streams. So.
No, that's true. Yeah, so you end up losing material, and so in some cases you potentially dissociate the halo completely. But obviously, if it's a little bit bigger, or it also depends on what the original trajectory is. So if you obviously come in and that you actually, don't go through the messy stuff at the center, then you obviously survive much longer. If you go straight down the middle, you're going to strip a lot of material. And so it's, this is where, simulations are really great, because we can bombard halos with each other and see that, okay, in, if these are our relative masses, or this is our initial, impact angle, this is what we end up with. And we actually see some of these streams, these kind of, this sort of stripped material, the kind of remnants of these collisions within our own Milky Way. And so there is like, if you look at this thing called Gaia data, which kind of keeps track of where the stars are, and people have really started, turned this into somewhat of a cottage industry where we look for remnants of these collisions in these structures. So yeah, we do have some analogy of planetary orbits, but it's a little bit more complicated. Does that answer that?
I think it does, and I think it sounds like a pretty straightforward question, but it is so complicated, and it ties into everything about how everything forms in nature, really, like this hierarchical form.
Yeah, and actually, as a fun kind of tie-in into dark matter, if, depending on how your dark matter actually interacts with itself, these streams might look different. So for example, if you have self-interacting dark matter, the stripping process might be more efficient. And so, by looking at the sort of streams that we find in our own Milky Way, we might be able to constrain how, if any, potential self-interaction exists with dark matter.
Oh, wow, that's so neat. Okay, so we've hit 8:30, but we do still have things planned. I know we're running a little bit late. I hope that everybody at home is able to keep hang out. The first thing is to bring Nick on. I think he's going to let everybody know what the answers to the trivia was. So Nick, do you want to take us through the solutions, and maybe I'll explain in question number 1 what my hint meant?
Absolutely. All right, here we go. Okay, so question number 1 was, what is the name of the comet that was visible through July and will not return to our skies again for another 6,800 years? Mark, explain the hint.
Well, the Oracle is speaking to Neo, of course, in the Matrix, and in their first encounter, she is talking about Trinity's love and highlights that Neo is not so bright, though. In fact,
there we go.
He is not wise. So
there we go. So the answer is Neowise, C2020F3. Neowise stands for Near Earth Object, and it's done through a wide field infrared sky explorer. That's what Neowise stands for. So the answer is Neowise C2020F3. Question 2. In the Star Wars Episode 7 movie, and later confirmed in a coloring book in 2016, the Star Wars galaxy found far, far away was displayed. What type of galaxy was it? And well, Connor gave us multiple different kinds of galaxies, and the far, far away galaxy was a spiral galaxy. Here's a picture of what artists think this galaxy would look like. We're going to leave this up here on the YouTube so that you can back up and read further details here. But going forward, question number 3. On August 2nd, 2020, SpaceX's Dragon capsule recently splashed down with 2 astronauts on board. It marked the first crewed commercial mission to and from the International Space Station. For this 2-point question, please tell us A, what was the month and year of the very first crewed splashdown return from space? And B, how many times has this landing been done? And the answer is the first ever splashdown back to Earth was on May 5th, 1961. So if you told us May and 1961, you get points. And B, how many times has this happened? The answer, 33 times. Question number 4. The sci-fi Netflix show Dark recently finished. Dark ties time travel, paradoxes, quantum mechanics, and more. In Dark, they feature a special particle, which is another name for the Higgs boson particle, the particle which is responsible for mass. What is the name for this particle? What is another name for the Higgs boson particle? The answer, it's called the God particle, which is humorously short for the goddamn particle. Question number 5. When was the first ever recorded observation of the Perseid meteor shower, which are visible right now in the sky? Maybe give it 3 hours or so. And the answer is AD 36. So quite a long time ago, almost 1900 years ago, more than 1900 years ago. And as said, we will accept anything between plus and minus 50 years. So you can go all the way up to 86 or BC 14. Second round. Question number 6. What is the name of the rover recently sent to Mars, which will, among other things, collect a sample to eventually be returned to Earth? And the answer is Perseverance. Mark, how does it collect back and bring back the sample?
So my understanding is it will be collecting the sample. It has a few different analysis instruments to be able to study different materials, but it'll find one that it wants to have come back to Earth as like maybe a promising sample to relate to maybe life that used to be on Mars. And it'll hold on to that. And then in the next couple of years, we'll be sending another craft to Mars to meet up with Perseverance, pick up that capsule, and then bring it back to Earth. And so this has been long planned as a Mars sample return mission. So this is phase 1 of that whole process. It's going to be really, really exciting. We've had samples returned to us from comets and asteroids. This will be the first time from another planet.
Wow, amazing. All right, question 7. Thanks, Mark, for that. Subsurface oceans have been known to exist in many moons in our solar system, including Jupiter's Europa and Ganymede and Saturn's Enceladus. Astronomers have now detected evidence for a subsurface ocean on a different solar system object. Name this object. And the answer is Ceres. Question number 8. In 2008, Hubble Space Telescope took the first visible light image of an exoplanet. What is the name of the exoplanet? Answer, Informal B, which they're still debating whether this is an exoplanet or not. Question 9. Which NASA space shuttle carried the Hubble Space Telescope into orbit in April 1990? 30 years ago. Which NASA space shuttle carried the Hubble Space Telescope? The answer, Space Shuttle Discovery. And finally, question 10. Christopher Nolan's next blockbuster, Tenet, is finally getting its time in theaters after a COVID-19 induced hiatus. In this movie, it seems like people can reverse time. Typically, Star Trek uses hypothetical particles with imaginary mass that can travel faster than light to explain anything to do with time travel. What is the name of the particle? And the answer, tachyons. All right. I think tachyons are also used in Flash. All right. So this
Tachyons
brings
are used
us
in
to
a lot of things. Definitely a major feature in the finale of Star Trek Generations. All good things. Really cool paradox that Picard has to figure out. But I love tachyons. I wish they existed. They're cool imaginary particles. But we don't know that they exist yet.
Thanks for everyone who played along in this trivia. We will have a look at the answers and reach out to the winners. That's right, Mark?
Yes, that's right. So obviously we will not be taking any more submissions at this point because the answers have been revealed. So as people submitted that form that was available in the YouTube description, we get a timestamp. So we'll be just using the people that submitted in advance. But now, I know that we're over time, but I really wanted to there were some extra questions that we didn't have time to get to, and this will be up in the video after in case people can't watch live right now. Maybe they can come back later, but I want to welcome back all of our speakers and just have maybe like a 10-minute discussion just in case people, like maybe our speakers had questions for each other, and then we do have a few leftover speakers. So Sarah, Kate, and Connor want to show their video and come and join us on this panel.
Hello.
Pop into existence like virtual particles. So I want to thank you all. You guys had such amazing and very interesting talks, all in the world of galaxies and the universe. There was one question I wanted to like start us off on, if I can scroll up on my list. I'm looking at the wrong spot. So there was a question about entropy, and this was to you, Kate. Is there a concept of entropy when it comes to dark matter? And maybe any of the panelists, like the beauty of the panel is, does anybody else have a feel for how to answer this question? This was from Jack Kraft.
Very interesting question. My instinct is that yes, entropy does apply to dark matter. So as we know, entropy increases. Oh, sorry about that. Entropy increases throughout time by definition. So I would say that that applies to dark matter as well. But if anyone wants to chip in.
Well, I would imagine that the time scale that entropy increases is a lot slower for dark matter, just because the forces that it uses to interact with are so weak. So although entropy would have to keep increasing, it would happen over such long time scales compared to like how messy my kitchen gets while making dinner.
Connor, I'm hearing that there's a bit of an echo from your computer. Maybe either muting yourself when you're not speaking or using headphones just for audio could be useful. Sorry about that. Yeah, so are there any questions between the speakers? Like, was there anything that was kind of inspired by the other speakers?
Yeah, I guess, I mean, I don't run any simulations myself, but I think they're really useful tools for what I'm interested in. But I'm just wondering, so we've kind of got these beautiful hydrodynamical simulations now. So being greedy, I kind of want to ask, sort of, what's the next step beyond that? So what's the next big innovation in cosmological simulations, I guess? What's the next big thing we want to include?
Ooh, that's a really good question. Some of the things that I'm more excited for are kind of just adding even more things, more physics that we know should be in these simulations, but we haven't yet modeled. So I showed you dark matter only simulations, but then as Sarah said, we can add hydrodynamics, so we can add gas and stars. And next we can add even more types of particles. So we can add neutrinos, which we think are have a decent impact on the evolution of the universe and on how galaxies form, but we don't know the exact masses of them. We don't know how much there is. So that's one that I think is really big these days, neutrino sims. You could also just kind of model the physics in more detail. So adding things like AGN, which you two were just talking about, into your hydrodynamic simulations to really get the feedback that you would get in your real galaxies, which then affects the entire structure of the universe. So those are some of the things I'm most excited about in cosmological simulations.
Yeah, I mean, maybe one thing put it forward would be, along with the physics, is just the computer power that we're now getting slowly and steadily. And so, yeah, getting better resolution, because with Illustris and things like that, and other simulations like Eagle that are around there, you can't really get down to, I don't know, people scale resolution. Well, and I'm not saying we have to go down there.
I think Kate highlighted that, like, the particles in our simulations are not actual particles. And I'm really impressed to hear that some simulations now actually individually resolve a single star, which is still like so inspiring when you think you're like resolving, in your box is big enough to get hundreds or thousands of galaxies in a representative little piece of the universe, that you're still individually representing stars is so cool. And I think through that, you can now have a better way of including all the physics that comes from an individual star, like the neutrinos that you mentioned. It's, it's the new technology, I think, that's going to really pave the way for our ability to bring in all these extra bits of physics, and physics, accurately represented.
That's right.
To tack on to the new technology and increasing computational power, I wonder, Kate, how are things going with using GPUs like people use for video games? I imagine that would be pretty helpful. Right?
Yeah, definitely. That is the next generation of simulations and all computational physics. So I think the next generation of simulations is, I think, already on GPUs. There's even newer kinds of processors that are specifically designed for these types of computations. So there's such thing as TPUs, I forget what that stands for, but you can get really specific in how you design your computer chips. Yeah,
so
thank you.
For us boring theorists, can you explain a little bit more what GPUs are and what they do?
Yes, great question. CPU is just your computer processing unit. GPU is your graphical processing unit. So it has more power. It can run things in parallel a lot more smoothly, which is one of the biggest things, because a lot of the operations, you're kind of, for example, computing the force between particles over here and over here. You can do that all in parallel. So it goes, hundreds and hundreds of times faster. But Connor, you seem to have a lot of knowledge here. You want to add?
Oh, no, I don't think I could add much more. GPUs are they're really just basic CPUs. They're tiny, and you have a lot of them all together, right? That's the idea. Yeah, I don't think I could add much more. TPU I just know about because they use those for neural network processing, and one of the standard codes for creating neural networks is called TensorFlow, and so that's how I know the connection there.
Connor, now that you're...
Oh, is my audio okay now?
No, it's not, because now that you're using your headphones, it's really poor. So I think if you're going to mute yourself, then you don't need to use the headphones.
Okay, I won't use the headphones.
So you had a question, Connor?
Yeah, if I could ask Sarah an impossible question.
My favorite.
I notice you always start your talks with some great philosophy, and I assume that you have a bit of a philosophy background. So how does your philosophy sort of feed into your physics and how you do your work?
Well, I mean, when I did my undergraduate in Auckland, I did a conjoint degree. So I did a Bachelor of Science and a Bachelor of Arts, and my arts major were maths and philosophy. So I was really lucky enough to have some really inspirational lectures. And so I did a lot of mostly metaphysics. So it's kind of like the study of why we know what we know sort of thing. And also a lot of 20th century existentialism, which is mostly about how terrible it is that we're all alive. I suppose so I want to kind of summarize that. But I think we're scientists, and that's a really important part of our identity. But we always have to remember that we're people first. And as much as we like to think that we're these kind of guardians of objective truth, ultimately it's still people who are motivated by very people-based things. And so I think thinking about who we are within the universe, and not just as an amalgamation of particles or forces, I think is really important, because it informs how we do science. And I think not necessarily that it will change, the mass of the electron or anything like that, but the way we discover the electron does have, or who discovers the electron can have some really far-reaching implications. And I think I tied in a little bit about, the point about, how all cultures have some sort of tradition of astronomy, but we have lost a lot of those traditions because, through the way, because we're dominated by this kind of Western thinking, the Western philosophical tradition, because, natural science was very much considered philosophy until everything started splitting towards the 20th century. And so I think us as scientists, we need to, obviously do good work and, be rigorous in the research we conduct. But I think we also have to make sure that we are, above average people. We've been kind of very privileged to be sort of given the keys to this, and we can't be gatekeepers. We have to share it with other people, and we have to share it with society. And so as part of that, and I think is we have to examine how we think and how social structures form, and how that informs science, and how that informs who has access to science. I'm not sure if that answers it, but yeah. Maybe it kind of also lends me to go on rambling, kind of pontificating talks. So, plus and negatives.
Yeah, no, a great answer to an impossible question. Thank you.
There's a question from the crowd for maybe, I think it was inspired by Connor's talk. which is, do spiral galaxies eventually spiral outwards? Or does like a galaxy collision stop that? Like what happens to the spirals?
All right, so
This is
as
from
for what
Schon.
happens to the spirals, I think it depends a lot on what kinds of spirals they are. From what I understand, these spirals aren't actual like a whole bunch of stars that are sort of going around in that spiral pattern. It's more of a density wave where the stars sort of come together and they're closer together for a while they're part of that arm of the spiral, and then they move on. And so the stars actually will go around the galaxy faster than the spiral arm itself will, which is sort of like a coherent structure coming out of all this chaos of stars moving around. So as for what happens to them, I think a simulator might actually be better at sort of answering that question, because you can play it over time. I just get to see individual images of galaxies, so I can tell you whether or not spirals are there. But as for how they evolve, that's more of a simulator question.
I have a follow-up question for Connor about machine learning and galaxies. I was wondering, because one of the kind of main criticisms of machine learning is that it's a black box. You can't really understand what it's doing. And so we might not want to just classify galaxies, but we want to understand what features the machine learning algorithms that we're using as like with the humans to train the machines are actually picking up on, and can we actually like learn new things about galaxies with these machine learning models?
Yeah, that's a great question, and that's really the question that comes up first when you're applying machine learning to any sort of topic. And so like anything else, machine learning is a tool. I like to think of machine learning as any sort of case where you're fitting a model to data. And in the case of neural networks, those models happen to be so complicated that, as you said, they kind of act like a black box. But we've tried sort of standard techniques for analyzing what a galaxy looks like, and it's really just too complicated of a question to answer with sort of rigid, simple models that we usually model our data with. So for neural networks, what you can do with them is, because they train fairly quickly, you can have it learn everything it needs to know about galaxies in like under a week. You spend all the time that you have left on validating the model. You test it on lots of galaxies that you've already looked at, like with Galaxy Zoo, and you can see how well it's performing. And you build into it some way to tell when it's not sure, when it's looking at a type of galaxy it hasn't seen before. And then it can flag those and you can look at them yourselves. So it can sort of become a filter where anything that's sort of routine, you know, you've tested it very strongly and you know it's going to do well. But whenever something unusual comes up that it hasn't seen before, it can sort of bring it to your attention. And now you can spend all your time looking at the really bizarre and interesting galaxies as opposed to the billions of them that are out there. So in that way, they become a very useful tool, but you always have to regard them with a little bit of skepticism. And there are ways to tease out what a neural network is thinking quote unquote. You can actually run the neural network essentially in reverse and sort of using random iterations, create an image that seems to activate some part of the neural network very strongly. And so you can get a sense, well, if this randomly created image activates this part of the neural network very strongly, that must be what it's looking for. So you may start with a noisy image and then over time create like a spiral arm feature in the top right corner of your image. And that happens to make one particular neuron in this whole neural network go crazy and light up really brightly. So now you know what that node is looking for. And so you can sort of do lots of this type of analysis, take an individual image run a neural network on it, and now you see, oh, these 3 neurons are all the most activated ones. And I know that those 3 neurons, this one looks for a spiral arm in the top corner, this one looks for maybe an X feature, kind of like what we're seeing behind Mark right now.
So I feel like we need an MRI expert here, because I feel like this sounds exactly like putting a brain under an MRI or whatever they use to like see how the brain neurons light up when you're looking at particular images.
You show an image to a human and you can see what parts of their brain light up, and it works the same way with neural networks. So people do that to sort of pick them apart and see what's going on in the neural network. And of course, people try and work in flags that identify when it's not doing well, when it's confused, maybe when a whole bunch of nodes are lighting up when only really 1 or 2 should. So I can go on and on about neural networks, but that's sort of the basics.
So I think we
really cool.
are able to go maybe another 3 minutes max. There is a question out there which is focused towards Kate, which is how do you represent kind of the expansion of the universe in your simulations? And this is from Eric Stacy.
Yes, that's one thing I swept under the rug. I had that big jar of dark energy that I decided to ignore. But the answer is that it's actually fairly straightforward, because we can just model our whole box of the universe as expanding along with dark energy. And so we can just kind of change our coordinate system into coordinates that just depend on how fast the universe is expanding. And then our dark matter particles are just kind of expanding with the universe, and we don't have to worry about it too much. So that's kind of the short answer of the really big effects of dark energy. But there are then the effects of dark energy on the large scale structure, which does affect the entire expansion history of the universe. And that's actually one of the parameters we're really interested in constraining. The Hubble constant is one of them, how fast the universe is expanding. And so it does also have more subtle effects on exactly how the matter forms, how this web behind me forms. And so we can actually use the result of this matter to understand those dark energy parameters.
Just so, since you mentioned H0, have you got any particular strong views about the H0 tension that everyone's being very excited about? So I should mention, so the H0 is basically that it's just a number that tells you how fast the universe is expanding, and we mostly assume it's constant, but different experiments are giving us different values, and they're getting very difficult to reconcile these with each other.
Yes, it's kind of now a fight between the early universe cosmologists and the late universe cosmologists, because those different observations are giving us very different results in high tension with each other. They can't both be right. So as someone who studies galaxies, I'm more on the late universe side, but I would say I'm not going to take a side here and put my professional reputation at risk one way or another. But do you have an opinion on that, Sarah?
I mean, as long as I can throw fun dark matter models at the problem, I'm happy. No. But could we use simulations perhaps to, because I assume you're just taking a H0 as a constant or some degree. Can you potentially vary those, or have you? I mean, obviously it's something very much non-trivial to run, but is there perhaps an avenue where we can explore what would look like if we have variable H0, and whether there are something detectable that maybe would help us shed some light on the problem?
Yeah, so that is that's actually a good answer to your previous question about the exciting new cosmological simulation. Mm-hmm. So one thing we can do is we can change the equation of state that governs how dark energy changes over time. And so those, I think, have been done on kind of smaller scales, but I think the next big thing would be to be able to run many different models of dark energy that change over time in these giant universe boxes, and be able to see if any of them slightly match our universe a little better. So that's definitely something that's on the horizon.
Another way that you can think of trying to reconcile this, I think, is maybe the idea that how you would measure the Hubble constant locally really depends on what your local universe is doing. So even in these simulations with a set constant, you could, if the simulation is big enough, kind of, okay, what if I was an observer on this galaxy? What H would I calculate just based on the local galaxies? And you can go over a whole simulation and say, what kind of variability can you get for that value, depending on which galaxy you're at? and just to get an idea of like how much variation is kind of okay in the Hubble parameter as observed locally compared to, say, you know, the distant early universe that Kate responded to. And as far as I know, it's not enough to explain this difference, but I haven't really been paying attention to that.
From what I've heard, that concept is called a Hubble bubble. Sort of, you're in a bubble of space that's all kind of moving or expanding, and it changes what H naught looks like. But modern measurements are going out farther and farther beyond the length scale where you might think a Hubble bubble could exist. Kate's nodding, so I think I'm getting it right.
Okay, so the last and not least question was for Sarah. What is the comic on your fridge?
Oh, hang on. This belongs to the previous tenant. It's a postcard. Oh, do you mean the thing in the back or the actual
I think
postcard?
they said the poster on your fridge or the
okay, so on the fridge, it's a postcard of St. John's Gate, and I suppose that's in France. I don't know. Sorry, I'm an astrophysicist, which means that anything local, I'm really bad at geography. But yeah. So I don't know. This belonged to the previous person. So I take no responsibility.
Fair enough. Okay, so I want to thank all my speakers again, Kate, Connor, and Sarah. Thank you so much for engaging with us tonight. Thank you to everybody at home, especially those that have tuned in right to the end of our 30 minutes plus extra features. And to anybody joining in, I know all of the speakers have said that they are happy to take any follow-up questions for people that happen to catch the video after the fact. So I'm going to change the description in the video to tell you how to email me if you have any questions for the speakers, and I'll relay that. The other thing I want to highlight is I think our next Astronomy on Tap event is going to be September 25th. So stay tuned for more information about that. And that's it for tonight. So thank you again, everybody. Alrighty.
So much, Mark.
Thank you. It was nice seeing everybody, and stay safe, everybody. Take care.
Thanks for having me. Bye.
And thanks to everybody at home.